Okay, the lecture today is on forging, modeling of forging. So first I introduce the forging process and I'll give some general consideration about the forging, and then the main concept, I talk about the main concept of forging and the terminology in forging process. Then I introduce the types of forging process and the die material, die failure in forging. And next we talk about some analytical approach to calculate the forging load, as we did for drawing and other process, because next week we will have simulation to calculate the forging load and some other aspects in forging. So this week we focus on the introduction of forging and introducing some equations for analytical approach, and a little bit about the microstructure in forging, and finally talk about the defects, the typical defects in forging process. Good. So I think more or less you're familiar with the forging process. The forging is defined as working of metal into a useful shape, into a final shape, into a required shape by hammering or pressing. So I can say that the forging is the oldest metalworking arts, and it's interesting. In fall we had a one day excursion to a city nearby Freiberg, and these photos, I captured these photos. It's a historic hammer mill, and it's interesting that the force is provided by a water mill in these types of historic hammer mills. It was founded in 1844, but this is not the only example. Even I saw another example in Freiberg. So if you are in Germany, in Freiberg, and you are interested, if you search, you can find and you can visit. But after industrial revolution, the types of machine and the way of providing the energy changed to like electricity. But however, the concept of forging and hammering was same. Today's the forging machines are able to making the very small parts in the micro scale even, and to the very big parts like the turbine rotor or the crankshaft, for example, of a ship. And there is no limitation on the size. However, the types of forging process, the type of forging process you use, of course, it depends on the size. And usually the forging process are carried hot. However, in some cases, for some materials and some special design, we have cold forging also. Okay, let's talk about the general consideration in forging. Okay, the animation is showing the forging of a gear, probably used in in a machine. But here, as an example, you can see in automobile, many parts are produced by forging. Okay, especially you can see it's many parts here in engine and in gearbox. The gears and and other different parts are produced by forging. A very important tips in forging is the mass production, especially if you want to produce your parts using a closed die forging. In that case, the number of production should be high. It should be mass production, because making the die and the forging process by itself is expensive. So production for a few number of parts, it's not economical. So yeah, the purpose of this slide is showing that how diverse are the forging parts. Of course, they are not limited to the automobile parts. In many other industries, even for decorative, for metals, for in missiles, in different industries, you can find some example of parts that are produced by forging. And I think this graph is interesting for you because you're studying the manufacturing, and this graph shows this place of forging and gives the details, all the details about the forging process and categories under the forging. I do not talk about the other parts. Okay, it starts from the manufacturing and the products and different categories you can make, but in the products, if you want to categorize the manufacturing process according to the products, then we have the metal forming here. But you know that casting, machining, we have other manufacturing methods, but we focus on metal forming. And then in metal forming we have bulk forming and sheet metal forming. Mr. Gayoom will talk about the sheet metal forming for two separate lectures in 2 weeks later. But under bulk forming, we have forging, extrusion, rolling, drawing, and other process. We have already introduced the rolling, drawing, and today we talk about the forging. Okay, under the forging, we can categorize the forging process with respect to the type of machine which is used. For example, press forging, hammer forging, screw press, automatic multi-stage forging, incremental forging, which is a type of forging which shapes the material incrementally, step by step, little by little, and then upsetter and so on. If you want to categorize the forging based on the die, then okay, die shape, then we have closed die forging, open die forging, and we will talk about these two because it's these are important terminologies in forging. And if you want to categorize the dies based on the type of motion they have, we have the rotational forging, translational forging, even explosive forging. This explosive forging is used for the forging with a very high strain rate. If you want to introduce forging under the material type, then we have the steel or ferrous forging and non-ferrous forging. Because we can forging started with forging of steel, but nowadays we have the forging for aluminium, for titanium, and other alloys. And according to the size and shape, it can be large scale, like as I said, for example, the crankshaft of a ship, which the length is almost 3 meter, and in common size, or in the micro size or micro forging, which are the parts are very small in the micro scale. Under the temperature, we have hot forging, warm forging, cold forging, even isothermal forging with constant temperature, and so on. This is another category. And then under the density, we have the common forging is like the bulk forging with the material we know, but we can even forge the powder. I can say it's a kind of powder metallurgy or powder forging. And based on products, the precision forging, and so on. So if you go forward in this diagram, in this flow chart, you can see almost all types of forging available. So I think even for me it's an interesting chart. So now you have an overall understanding on the forging process. Now we go deeper and deeper, and so you become familiar with the process. Okay, let's go to concept of forging and terminologies. This is also important because if you want to understand the process, you should know the terminology. For example, here, usually in forging, the billet comes from a rod. We cut the rods into the billet, we call it billet, and then using one open die forging process, we prepare this barreling shape. Usually it's not the same for any cases, but usually it's like that. Then we call it preform or pre-shape, and then the operator put the pre-shape. Of course it could be hot. It's hot. We put it between the dies. Here you have the upper die, the lower die. Here the lubricant for to reduce the friction. The force is applied by the press machine, and the dash line is before applying the force, and and after applying, you can see even it shows some deformation in the structure of press. It's interesting. Maybe you couldn't imagine that when you're forging a material, even the machine have some deformation. Of course, this is exaggerated to see, but it exists. So the structure of the press is important, and the stiffness is important. And then after forging, this is the forged material, and this part we call flash. I talk about it here in detail. Usually after the forging is not one stage, usually preform and then 2-3 stages, maybe it depends on the design. And then you have a flash here. You should trim the flash, remove it, because it's not in the design of the workpiece. It should be removed, and then finally some heat treatment, and the final product is ready. In detail, here you can see the terminology for die or for forged part here. This area we call it rib usually, and here is called web. This is fillet. It's clear for you. This is corner. This is the trim line, because the flash is trimmed at the final stage in machining stage on this line. And then on the flash we have the flash gutter here, and the land here, and also die should have a parting line, because die should be open, and the operator should be able to take out the part. Okay, and on the terminology, I think I have covered almost all the points. We can proceed to the next slide. This slide just introduced a few types of forging machines or forging press which are used. The press types is not limited to this, but I just want to introduce like the drop hammer, which the ram just drops under the gravity force, and the screw press so it's a mechanical system to apply the load, but it's a mechanical system apply the loads by like rotating this wheel here, and then flywheel, and so it has a motor here. And a crank press, you can see the crank press has a crankshaft here, so by rotating the crankshaft it applies the force. The force is applied, the force is a combination of gravity force and also the force applied by engine. And finally the hydraulic press, you can see here, okay, it's clear, the force is applied by hydraulic system, as you can see in the figure. So if you want to compare these different types of forging machine, you can see that the available energy per blow is in drop hammer is the minimum, but in hydraulic press is the maximum. So you can apply the maximum energy by hydraulic press. However, we have another parameter which is important in forging, is the velocity of the machine, or I can say that the strain rate we apply. Why it is important? Because you know that the material formability depends on the strain rate first, and second, usually the forging is a hot process, so the time which the workpiece is in contact with the die is important. So when the forging speed decreases, the contact between the workpiece and the die will be longer, so you will have a higher heat loss. And then, okay, according to the heat loss, the mechanical property changes, the force and the microstructure, everything. So the speed is also important. The hydraulic press, you can apply the highest energy, but the speed is the minimum, as you can see here. So according to your design, according to the part you want to produce, according to the material you want to forge, you should choose the appropriate forging machine. Okay, so how we can design a procedure of forging process? Of course, now today, because we have computer and simulation, it starts with modeling. Maybe before having this technology, they had to just try and error in design, but now we can do the try and error using the simulation. So first we model the part, and then we design the die conceptually, not a full design, but a conceptual design of the die, and then we can run the simulation. We will see some example of forging simulation next week, and then we can optimize. This optimization means from the very simple view, for example the billet size, billet volume, the initial size of the material should be enough to fill the die. So how much should be the volume of the material? How should be the shape? For example, okay, after you decide about the size, then the billet, for example, your billet could be like this, of course, cylindrical. So you have a diameter here, D, and the H. So what should be the D to H ratio? Based on the material flow, based on the flow lines, you can change this shape, keeping the volume constant. So this try and error can be carried out here using the simulation and forging simulation. And when the process is final, then we can go to the designing the die details, because the die is not just die cavity, but the injector, the other parts of the die should be designed using the CAM, and then we can fabricate the master gear. Master gear means the gear before machining, and then it goes to the machining step, and then evaluation and quality control, and then tryout. So this figure also shows these steps, the types of machine which are used, the die, the design of the part in the model, and so on. And here you can see the comparison between the model, the simulation, the predicted. I don't know what is predicted here. Okay, but you can compare, and even the direction of the workpiece, putting the workpiece into the die is important. Sometimes during the deformation you rotate the billet, for example, after the first stage or second stage, then you rotate it 180 degrees upside down, and then another step. This also could be designed just to optimize the metal flow line, and or I can say to optimize the mechanical properties, and sometimes to minimize the forging load. Okay, and then, as I said, forging is a hot forming process usually. So the material property and the material flow property clearly depend on the temperature. So this figure shows that, for example, for this type of steel, STB2 steel, this is the result of tensile tests from 900 to 1250, and you can see above from 900 to 1100 or 1150, the reduction ratio is almost good, but then even above the temperature, the reduction ratio decreases. So conclusion is that for this type of steel, the deformation temperature is in this area, because it's showing a good formability or forgeability. Below this is not good, because the formability is not good, and of course above that temperature you will have some other kind of problem. So forging temperature range, for steel, it's for all the steel, it's like between 900 to 1100, depends on your steel type and your design, of course. And okay, this figure talks about shows the metal flow line and how much the metal flow line is important. The distribution of metal flow line should be homogeneous, and if the distance between the metal flow line, like here, decreases in your simulation, then you should expect such a failure, such a crack in your part. As you can see here, it's a kind of internal crack. We talk about this type of crack in forging parts defects later. Okay, types of forging process. Generally, we have two categories: open die forging, closed die forging, and of course, we can add the third category, which is impression die forging. However, this closed die forging and impression die forging are almost similar, a small difference, but the open die forging and closed die forging are totally different. As you can see, okay, the name shows that open die forging, you do not have designed a die. The deformation is carried out between two simple dies. It's like offsetting, as you can see here. But in closed die forging, you should design the die, and more detail will be transferred to the final product during the forging process. And in impression die forging, of course, you will have much more detail in the die. Then you will have the flash part and the flash land and gutter, everything. All the terminology we introduced, you can see here in impression die forging. But this animation shows that usually the open die forging is the first stage of forging, is the stage which you prepare the pre-shape or the pre-form, and then later usually open die forging is followed by a closed die forging. This is open die forging, and the second stage is a closed die forging to shape the material to the desired form. This animation also shows the forging of a crankshaft, as I said, and you can clearly see how the flash forms during the forging. Of course, this is a closed die forging. Again, closed die it does not mean fully closed. If you have flash, still it's a closed die forging. And later we will explain that why we should design a flash area and why we need the flash. And if you do not design the flash, what may happen? Okay. The other type of open die forging, beside the offsetting, you may have the other type of open die forging. You can see here, for example, forging a large turbine shaft here, and these flat dies is hammering the material, and the length increases, so you can shape your product step by step. But okay, anyway, because it's open die forging, so the material is deformed between flat dies, and dies are very simple in open die forging. The process is mostly used for the large objects, and when the number of the parts produced is small. Okay, when the number of the part is small, it's not economical to design a closed die forging, because as I said, that try and error to design the die and then making the die by itself, the machining, it's a very expensive process. So if you want few parts for 10, 100 something, then you should find the other solution to produce. For example, machining is a solution, but you know the products produced by machining has not good mechanical properties. So the other solution is that, for example, you apply a big deformation in an open die forging, for example, and then start the machining on the preform. But the waste of material the waste of material is high in this, because you should machine and remove a big part of the material. And the other solution are such a process. You can see in the figure, for example, if for a turbine shaft, or here for forging a vessel cylinder here. On the other side, we have the closed die forging, or here, because all these characteristic, we can allocate it to the closed die or impression die forging. So in this category, the workpiece is deformed between two dies halves, and which carry the impression of the desired final shape. So all the details are transferred from the die into the workpiece. So this is an advantage, because the machining time and machining cost decreases, and the mechanical property, of course, if you design it well, increases. But of course, the workpiece is deformed under the high pressure. This high pressure leads to a higher mechanical properties, and it's normally used for the smaller components compared to the open die forging. When it's too big, so you cannot design the die, a big die, or not you cannot, but it's not easy to design a big die for the closed die forging. The dimensions are precise in closed die forging, but as I said, it's expensive. The designing and designing the process and making the dies are expensive. So you should think about it before. If it's a mass production, the number are high means like in the range of million parts, then okay, you can think about the closed die forging. And that, okay, this shows that some terminology in closed die forging. We talked about the flash, the component, everything, upper die, lower die. The only thing you see here is the ejector pin, and the ejector pin eject the workpiece after finishing the forging, because it's deformed under high pressure and high temperature. So the workpiece sticks to the lower die usually, and the operator cannot remove it, cannot bring it out. So the ejector is needed. So eject the component or the workpiece, and the operator can bring it out. Okay, in a general view, so in closed die forging, first you have a billet, and then pre-shape. Pre-shape is usually like by offsetting, as I said, and then a rough forging. Rough forging, here you can see it's not necessary to transfer all the details in one stage. So you can design it in 2-3 stage or 4 stage, depends on the product design. But so you may have a rough forging first, and then another stage, finish die, which the form of the component is almost close to the final shape, and I think this is repeated. And then the trimming is, as I said, for trimming the flash, separating the flash from the components. Next week we will check some forming load diagram versus the forging stroke. A stroke means when the ram is coming down and the deformation is proceeding, then this forging stroke or the time, this axis could be forging stroke in millimeter or the time, of course. Then okay, before contacting the die with workpiece, you have no load, and then when the die becomes in contact with component, then the load started to increasing, and then the more contact between the die and the workpiece, this load increases up to here, which I can say that the cavity, the die cavity is filled by the material, and this sharp increasement is because of the squeezing out the material from this land into the flash part. So here the flash forming starts up to the end. So this is the definition of flash. We can say the flash is the exceed of material which squeezed out of the cavity as a thick ribbon of material, as you can see in the figure. So why flash, and why should we design, not should, but I can say in most forging process we design flash. Some special forging process like precision forging. In precision forging, no need to design a flash, but it has its own consideration, and so I will explain that if you do not have flash, then your design would be so tricky, because the flash first acts as a safety valve for the exceed material. Okay, I said that in the stage of designing, okay, we by simulation we obtain the size of the initial workpiece or initial billet, so we can be sure that how much will be the how much the cavity will be filled by the material. However, in practice, sometimes the billet size may be a little larger. In that case, if you do not have flash, then because the material is big, if the cavity is fully closed, and then the material has no space to escape. And if the material is a little bit larger, then a very high pressure will be applied to the dies, which leads to the die failure. So if you design the flash, you will be sure that this type of die failure, I can say, or die breaking, you will not have. The other function is build up high pressure to ensure the metal fills all recesses of the die cavity. What does it mean? Later, when we go to the analytical calculation for the forging load, we obtain an equation which shows the that this is okay. Imagine that this is, assume that this is A and this height is H. This ratio A to H is important, so it controls the forging load. Here this ratio is not too big, but here this A to H, because H is so small, A to H ratio is big. So the flash is designed in this way intentionally, so it can apply some reverse force, and then the material will fill the die instead of skipping. So maybe a part of material is squeezed out, but before squeezing out, you can be sure that here the die cavity is filled, because the load which is required to push the material throughout the flash area is much more higher. So first the workpiece should be formed and the die cavity should be filled, and then the flash will be filled. But if you design the flash at the right position, at the right location and with the right dimension. I mean the ratio of A to H ratio. The remark is necessary to achieve the complete filling of the forging cavity without generating excessive pressure against the die. So if, okay, I said that we have some precision forging, for example. In that case, you do not have the flash area, but you should know that in some parts of the die, you will encounter with a very high pressure on the die. So die should be stiff enough, and then usually the die life decreases in that kind of forging process because of the intensive and high die wear. This is an example, a practical example, and the two designs for a part here. This is the part after the machining. Before machining, in the first design, you can see how big is the flash here. Okay, this part is the flash part in this design. But then after some optimization using the forging simulator, then we could reduce this size of flash into this small, and it's a kind of I can say minimization of scrap or flash, and or moving toward the green manufacturing, because less material, less energy is used. So I can say that this is an example of optimization using the forging simulator. Next topic is the die material and die failure. We just talk about it shortly. Die material properties which is required in forging is as follows. Thermal shock resistance, because as I said, usually in the forging process, the initial workpiece comes with the temperature of 1000, assume that it's 1000, and then after forging, when the operator removes the workpiece, then the temperature will be around 200, 300 something, and again the next part, again 1000, 300, 1000, 300. So repetitive temperature change or temperature cycle we will have for the die in forging. So a thermal shock resistance is very important, and a thermal fatigue resistance accordingly, because you know we have a type of fatigue which is called thermal fatigue. It's generated because of the repetitive thermal change, temperature change. So die should be able to tolerate this thermal fatigue. Of course, the die needs a high temperature strength because it works under the high temperature condition. Die should have the high wear resistance and high toughness, of course, and ductility, because the die should not be brittle because of the high load which is applied on the die. Of course it will break if it not be tough or ductile enough. On the other side, the hardness of the surface is important. The surface of the die, surface means, for example, here on the surface, should be hard. So the high hardenability is important. You should be able to harden the die on the surface, and in appropriate depths, but not too much. Just a surface hardness is required. This surface hardness can be achieved by some carburizing or nitrizing or coating the surface of the die, of course. And the other factor is the high dimensional stability during the hardening. So as I said, the die, of course, the forging die requires heat treatment. And if the material you are using for making the die does not have a high dimensional stability, so during the hardening it will some distortion will happen in the die. And you know, the heat treatment usually is the final stage, or the stage just one polishing or finishing after the heat treatment you have. So if the material you have used for the die shows low dimensional stability during the heat treatment, then the die will be distorted and you cannot use it then. And finally, high machinability. Of course, you should be able to machine the die easily. The example of the steel which are used for the die in forging process are alloyed steel, usually with high chrome, molybdenum, tungsten, or vanadium. We call this group of steel tool steels, and usually the heat treatment such as nitriding or chromium plating, a kind of surface treatment, are applied to increase the die life, to improve the die life. Based on your process, you can select the material for the die. If you want to produce the small tools, then you can use the carbon steel with high carbon as die material. If it's for hammer dies, then you should use the medium alloy tool steel. And in the case of if you want to use the process and horizontal forging machine with a high pressure, then the highly alloyed steel are required. These figures are some example, shows the example of the die for a crankshaft, as you see here. Not only the cavity, but some other details for the die are shown here, and it should be okay. It's a crankshaft of the ship, as I said. So you can see the length of the die is almost 3 meters. So you can imagine that how huge is this part, 3 meters, and how big should be the press and how strong should be the press which produce such a part. We have different kind of die failure. You can see in this figure die wear or abrasion. This is the symbol for this type of failure: thermal fatigue, mechanical fatigue, and permanent deformation. So using this symbol, you can understand that which type of the failure may happen at which area of the die. For example, here, because the material is escaping out under the high pressure, of course you will have the wear and some deformation, a combination of wear and deformation. Here just wear, here thermal fatigue on the web, and so on. So you can check, and this figure shows the probability of this failure, the different type of failure on different parts. Of course, it's important that the shape of forging, the die material, the way you heat up the workpiece, the coating of the surface, and the forging temperature or the operating temperature, and some other factors are important. For example, the forging temperature should not be higher than the annealing temperature of the die. If so, then the die will be annealed little by little during the time. So maybe after a week or after a couple of weeks, you find that the die is not hard enough and it starts to deform during the forging process. Okay, now we arrive to the mathematical part of the lecture, which is about the analytical method we can use to calculate the forging load. Of course, I just introduced a few methods, but the methods, of course, are not limited. There are some basic basic methods for calculating the forging load. As you know, the total energy in any deformation process is composed of the idle energy, the friction energy, and the redundant work or redundant energy. We talked about it before. The redundant work is the work that does not contribute to the change of shape of workpiece. It's the extra work, but it exists. So you should you should bring it into the calculation. So we can define the efficiency or eta here in the deformation using this equation, the ratio of the idle work to the total work. This ratio is between 0.3 to 0.6 in extrusion, but in rolling is much more higher, 0.75 to 95 almost. And it shows that in rolling process, the share of the redundant work is not too much, the frictional and redundant work. On the other side, in forging, you can see that this efficiency is so low, and the share of idle work, the share of frictional work and the redundant work is so big. So we can do the calculation of forging load under three main assumptions. In the absence of friction, in the low friction condition, or we call it the lower bound method, and under the high friction condition assumption, which we call it the sticky friction condition. Usually the reality is something between this low and high, this lower bound and upper bound. So this one underestimates the load, this one overestimates the load, but in reality the forming load is something between these two. In the case of idle form, which in the absence of friction, it's so simple. Okay, you have the definition of pressure here. The force is, of course, is just compressive force, and then you have the initial geometry, the final geometry using the volume constant. Then you can develop such an equation. And beside this equation, of course, you have the definition of engineering strain, true strain, and the equation, the relation between the engineering and true strain. So using these four equations, you can simply calculate the forging load in the absence of friction. It's a kind of rough estimation, but it's not enough. So to improve it, then we can use the forging load at the low friction condition. So now we apply the friction, but the friction value is small. How we can apply it? We apply the friction on the offset forging as shown in this figure under the plane strain condition, and of course the rigid plastic behavior. So the elastic behavior is excluded, and the plane strain, what does it mean, plane strain here in this figure? It means that, okay, when you're pushing the material can just flow in this direction and that direction, and here in this face and the face behind are fixed. The material cannot flow in the Z direction. I can say here is that in Z direction. So you have the die movement in Y direction and some lateral material flow in the X direction, right? Yeah. So to calculate the total forming load in this approach, we have to determine the local stresses needed to deform each element. What does it mean? So we consider an element like it's shown here in the figure, and then we calculate how much load is required to deform the workpiece with the height of h and the width of 2a as okay. And we talked about it already. This is under the plane strain condition, and we assume that no redundant work is performed here. It's a rough estimation, but okay. Let's see. So you have a vertical force. How you can calculate the vertical force? Simply by multiplying the sigma y to dx, and then for calculating the frictional load, then you need the mu or Coulomb friction coefficient. So simply you can calculate the friction component here, and because you have these two sides, then you multiply it by 2, and for calculating the force on these two side plane on the right and left, then you have sigma x multiplied by h, and sigma x plus d sigma x multiplied by h. Of course, we exclude the a here because all these terms should be multiplied by a, for example here, but we exclude it because then it will be removed from both sides of the equation. When you are writing the equilibrium in x direction, then you can write the equation in this way, and after simplifying the equation, then you can obtain such a differential equation. Okay, but this is sigma x, sigma y. How we can simplify it more? We use the yield criterion in this way, and because this term of the friction force is smaller, much more smaller than sigma x and sigma y, then we exclude it from the yield criterion, and we can write the yield criterion simply in this way. So sigma y minus sigma x equals to this value, which is the yield stress in plane strain. Okay, if you differentiate this equation, then you can obtain that d sigma y is equal to d sigma x. Okay, so if you put it here, not here, then the equation can be obtained in this form, that d sigma x, d sigma y to sigma y is equal to, now you can integrate, after integration, then you have ln sigma y equal to the term on the right, but now you have a constant c0 here, and you know, or you can write it in the exponential form, but you know that we should obtain the c0, the constant value, using the boundary condition, of course. So the boundary condition, we can apply the boundary condition on two left and right plane, x equal to r and sigma x is 0. When you apply it, then you can obtain such a term, and then when you apply this to the equation, then you obtain the c value, the constant value. Put the constant value into the main equation, c0, and you obtain this final form of the equation. Of course, it's not the final form, but okay. Now, at least it's not differential equation, and you have no constant to obtain. It's clear now. So if you plot this equation, it will be like this. We call it friction hill. Friction hill. So it shows that if you have offsetting, for example, you have the maximum friction in the middle, and to the sides, on to left and right side, the friction is almost 0, as we applied in the boundary condition. So we call this as a friction hill. This is the terminology used for this. So you can plot the friction hill using this equation, and of course the form of friction hill changes by changing the A to H ratio, and the friction coefficient also is important. Okay, to calculate the forging load, so we can write the load in this way by this is the width of the workpiece, and P bar is the average forming pressure across the workpiece. And then using the equation we obtained in the previous slide, and of course we can simplify this exponential term by using this series, and as the mu value is very small, then we can ignore all this term and just use first two terms and substitute it in this equation, and then we can remove the exponential term. Okay, then if we substitute the sigma y value in this equation, then we have this form, and you can integrate and obtain the forging load value. What this equation shows is that the A to H ratio is important here, beside the mu or friction factor. It means that, okay, I talked about it when I was talking about the flash part. So this A to H ratio determines the forming load or the forging load. If A to H ratio increases, the forming load rises rapidly, and the flash on the forging part is a good example of this behavior. Okay, this calculation is clear. I think it's clear. If you review it, I can understand. You can understand it. If there is no question, then we can proceed to the forging load at high friction condition or a sticky friction condition. When the friction force is high, then we can write the equation in this form, and it's based on the equation we obtained in the low friction condition, and then the mean forging pressure can be obtained using this equation. I do not bring the calculation for forging load at high friction. Is similar to the calculation for the forging load at low friction condition. However, this is the final equation, and this equation shows that under this condition the forming load is dependent on the flow stress of material and also the geometry. So in the low friction condition, it was dependent on the geometry and the friction factor, but here it's dependent on the flow stress and the geometry. For example, as you can see that if the A to H ratio is 8, then this forging, the forming load could be 5 times of flow stress. So what does it mean? It means that the local stress on the tool can be therefore very high, and it probably could be enough to deform the die. Of course, in cold forming operation. However, you should remember that this is under the high friction condition, a sticky friction condition. But in practice, usually it does not happen. A sticky condition means when the material sticks to the die, it means that the friction is very high. So, but you know, in practice, we increase the temperature and we use the lubricant to avoid such a condition, because in this condition the die will tolerate a high pressure. But in cold forging, because temperature is low, sometimes this sticky condition happens. So if it happens, then you have a high potential, high risk of die deformation. So how we can solve it? Of course, we should reduce the friction somehow by applying the lubricant or changing the workpiece geometry in the way that decrease the forces, or reducing the sigma, the flow stress of material. How we can decrease the flow stress of material? By, for example, increasing the temperature, and sometimes by changing the strain rate. You know that the flow behavior depends on the strain rate also. It depends on the situation. You can choose one of these solutions or all together to avoid sticky friction condition. So then we can continue the calculation for sticky friction condition in this way. Then some simplification on the equation. You can simply follow the equation and then integration, and then again you should obtain the constant at the boundary condition. You can obtain the C value and then the final equation. So you can see 3 terms here: A, H, the geometry, and the flow stress of the material are playing the main role in this equation. Okay, that's on this level is enough for the analytical calculation. As I said, of course, there are many other approaches for the more accurate calculations, bringing the redundant work into the calculation, and but just I wanted to introduce the analytical approach, not to go, and we do not have time, of course, to go to the deeper. And the next topic is the microstructure in forging. Of course, microstructure is important because the mechanical properties of your forged part is directly depend on the microstructure. This figure shows that if you produce the part using the forging, you can see the grain flow or the metal flow line as I introduced before. But if you produce it using the machining, you cannot see such a metal flow line, and this is the casting. So in the forging, you will have some elongation in the direction of deformation. And the metal flow during the forging provides the fibrous microstructure. You can see here exactly. This is a practical example. This is the simulation, but this is the reality. So you can see the metal flow line and the metal flow and how the grains are elongated in the direction of deformation. The structure gives a better mechanical property in the plane of the maximum strain, but of course, lower properties across the thickness. So it's important that this metal flow line is, for example, is parallel to the surface or is vertical. If it's parallel to the surface, then it shows a good resistance to the cracking. But if it's vertical or not vertical but almost vertical, then there is a high potential of crack at that point. Of course, if you have a hot deformation, then the workpiece often undergoes the recrystallization. Recrystallization leads to the finer grain and the higher mechanical properties. So we have a kind of redistribution of material structure in the forging. For the material flow, we talked about it, how the material flows. These are two other examples, but in the case of inclusion, you have two kinds of inclusion. The soft inclusion may be deformed during the forging, but the hard inclusion may be break down into smaller pieces, and sometimes in between some voids and some cavity will appear, which degrades the mechanical properties. We have another term which is called residual stress in forging. Residual stress produced in the forging as a result of inhomogeneous deformation. And usually these residual stresses are small because the deformation is normally carried out well in hot working. If it's cold working or cold forging, then you will have a high residual stress. Okay, so we have two kinds of residual stress. One kind of residual stress created during the deformation, but because the forging is a hot process, usually we do not have it. But we have another type of residual stress which is generated in the heat treatment or in the quenching. It means after the forging process. Usually we have such a residual stress, And as a result of residual stress in large forgings and in the middle area where the high hydrogen content, we have a high hydrogen content, usually some cracks appear in the middle at the center. This crack is a result of this high hydrogen content and residual stress together. This coupling these two leads to that central cracks in big forging parts. And of course the large forging parts should be slowly cooled down, because if you cool it faster, then higher residual stress you will have. So in the conventional way, they bury the forging in the ash, or you can put it in furnace and cool it down slowly. And the final topic is the typical forging defects. I have summarized the different forging defects in this slide. So the first defect is incomplete die filling. It means that the die is not filled. It may be because of your wrong calculation for the volume or some other problem. Die misalignment, the die are not aligned well. So forging labs or some cracks on the surface, or incomplete forging penetration, microstructural difference means that microstructure is not homogeneous. Of course, in the forging, without heat treatment, you cannot obtain a very full homogeneous microstructure. However, you can design the forging process in the way to decrease the inhomogeneity in the microstructure. Hard shortage, pitted surface, the small pitting on the surface, buckling in the case that you have a long part to forge. Sometimes instead of forging, buckling happens. Surface crack, micro cracking, flash line crack, and some of them are presented graphically here. This method, we call it the fluorescence or ultraviolet method to show the surface crack in the forging. So you can see here some they immerse the part in the fluorescence material and then put it under the ultraviolet, and then they can detect the surface crack in this way. Or the internal crack, as it's shown here. However, you can predict such a crack using the simulation. Cracking at the flash, as it depicted here, and cold shot here, it means that the material is folded somehow. So this is the surface of the material during the deformation. Now it's located inside. We call it cold shot. Then using the metal flow line, you can control this defect and to change your design to avoid such a defect. And so internal cracking also. So I think we are almost done, and I covered all the required topics on the forging in today's lecture. Next week I will bring some examples of forging simulation, and I think if we can go more deeper, even we can talk about the grain size, because up to here we talked about predicting the load, like drawing load, rolling load, forming load. But I try to talk about another stage, another level of using the simulation and predicting, for example, the grain size or some. Okay, that would be more interesting for you maybe. Okay, if there is not Is there any question? Okay, so if there is not any question, then I close this session on the modeling of forging, and see you next week for talking more about simulation of the forging process. Yeah.